In this video, we discuss about the basic concepts of nonlinear dynamics. We start by defining a nonlinear dynamical systems, an autonomous system, phase space trajectories, fixed or equilibrium points, and we study fixed points in one dimension. A dynamical system is any system whose state evolves in time. The state of the system at a given time is specified by the values of all the degrees of freedom. Our goal is to predict the values of all the degrees of freedom at any later time for a given initial values of all the degrees of freedom. The state of the system is defined by a set of d dynamical variables denoted by x1 of t, x2 of t up to xd of t. The dynamics of the system is decided by the set of decoupled differential equations given in equation 1, where fi are the functions of the degrees of freedom and it may also depend explicitly on time. When none of the functions fi show explicit time dependence, the corresponding dynamical system is referred to as an autonomous system. In this video, we restrict ourselves only to autonomous dynamical systems. The d-dimensional space spanned by the dynamical variables is called the phase space of the system, where the state at a given time is denoted by a single point. As time goes on, the state starts to evolve according to the dynamical equations, thereby tracing a path in the phase space. This path is called as phase space trajectory. A dynamical system is said to be linear if all the fi's are linear in the variables xi. It is nonlinear if there exists at least one fi that is not linear even in one variable xi. Let's define fixed or equilibrium points. There could be special points in the phase space such that if the system starts to evolve from such points, it does not evolve at all. It remains in the same point in the phase space throughout all the time. Such points are known as fixed or equilibrium points. Fixed points can be denoted by solving the set of equation. We equate all the dynamical equation to 0. This gives the fixed points that is given in equation 3. There could be several fixed points in the phase space for a given dynamical system. On starting slightly away from a fixed point, if the system eventually approaches the fixed point in time, then the fixed point is said to be stable fixed point. If on the other hand, if the system moves away from it, then the fixed point is said to be unstable. Let's see that in the one dimension. In one dimensional, the dynamical equation reduces to equation 4, for which let's call the x bar is the fixed point which satisfies f of x bar equal to 0. To analyze the nature of stability of this fixed point, whether it is stable fixed point or unstable fixed point, one needs to consider the dynamical perturbation around it. That is, let's take x of t as x bar plus delta x of t. The delta x of t is very small. Substitute in the equation 4, you will get the dynamical equation for delta x, that is given in equation 5. By neglecting the higher order terms, we can solve the equation 5 and we get the dynamical evolution of the perturbation, that is given in equation 6. This clearly shows that the perturbation around the fixed point decays exponentially with time for derivative of the function df by dx at x equal to x bar is less than 0, and move away for df by dx at x equal to x bar is greater than 0. Therefore, the fixed point x bar is said to be stable for df by dx at x equal to x bar is less than 0 and unstable for df by dx at x equal to x bar is greater than 0. For df by dx at x bar equal to 0, at x equal to x bar equal to 0, then the linearization method of deciding the stability eventually fails. One needs to examine the higher order terms for analyzing the stability of the fixed point. In the next video, we will study the fixed point in higher dimension. Thank you.